Welcome to this video on the topic of exponential functions. In this video, we're going to have a look at a special phenomenon known as exponential growth. Now, exponential growth is the name given when modeling a situation whereby a quantity increases through successive multiplication. Now, to get some context, we're going to look at a situation of the transmission of a pathogen known as flu virus. Now, this is a contagious virus in that for this particular strain seen over here, for every day that goes by, we're going to see an increase of 50% cases per day, or 50% infections per day. Now, if we consider that on day 0, we started with 1 infection, then what that means is that on day 1, so 1 day after the first infection, we're going to see a total of 1 multiplied by 1 plus 50%, also known as 0.5. Now, putting this in our calculators to calculate how many cases this is, it's 1 times, so 1.5 cases, so it could be 1 case or it could be 2 cases, we don't really know, but at any rate it's going upwards. So that's on 1 day since the first infection. Now day 2, the infection's going to grow even further. On day 2, it's going to be 1 multiplied by 1 plus 0.5 times 1 plus 0.5. So the cases from the previous day are going to increase by 50%. So 1 plus. This is going to yield a value of 2.25. So there's at least 2 cases in this instance. Now another way we can write this is we can go for the next situation onwards. For 3 cases we can go 1 times 1 plus 0.5. Then rather than writing them all out, I'll just put in a little cubed. So there's 3 instances of this. Computing this on the calculator, we're going to get at least 3 cases, so 3.375, so we're approaching 4. Now this can go onwards, or we can find a simpler way of expressing this, and we can just say that n, so on day n, we're going to expect to see 1 multiplied by 1 plus 0.5 to the power of n. Using this little formula here, we're able to determine the amount of cases on any given day. So if we go to day 15, we're going to have 437 cases, so it's starting to get out of control. Then on day 25, if we don't do anything about this, we're going to have 25,000 cases. Now this is all well and good, but a better way to be able to model this is using a graphical model. So what I'm going to do is I'm going to get this information shown here and I'm going to put it on a Cartesian plane. Now modeling this out, on our y-axis I'm going to call it I for infections, so say infection count. And then down here we're going to go t for days. Days since first infection. Now allocating numbers to the t-axis, we're going to start at 0 down here. Then we're going to go up by 2s, so we'll go 1, 3, 4 and 5. And then for my y-axis, I'm just going to go up by 1s, or I'll go 1, 2, finishing at 10. Now transferring some of these values seen over here, down to here, on day 1, or I should say on day 0, we had 1 infection. So day 0, 1 infection, we are here. Day 1, so 1 day after, we're at 1.5. If I bring this in, 1.5 seen over here. So that's roughly day 2, we're at 2.25, somewhere around here. Day 3, we're at 3.375. We'll go to day 4, 5.065, so roughly 5, it's starting to take off. And then looking at day 5, we're at 7.593, so 7.6 roughly. And we'll just clean this up to 1 decimal place. Reason for that is I don't believe I'm as accurate as I'm writing, so 1 decimal place will do. Alright, next thing I'm going to do is I'm going to draw a curved line to fit through all of these points. So sketching as best as I can. Alright, not too bad. And this is what we end up with. So this is our curve here. Now the curve itself is only as accurate as the points, but what it does show us is a sort of trend of what we're expecting to go on here. So what we can see by this trend is that the amount of cases is increasing or growing at an increasing rate. Alright, now since we've got this, what we're going to do is we're going to use this graph over here as well as this information to deduce the equation that describes this particular model here. So this infections per day, or I should say infections versus days. Alright, now the way in which we can build a mathematical model is that we know we're going to get I equals A multiplied by B to the power of, in this case, T, because we're working with I and T. Now the way in which we're going to deduce the value for A is we can either look at this value over here, or we can look at this value over here. Thus our value of A is going to be 1. And then to look for B, our successive multiplication rate, we're either going to look up to here, or we can look inside of here. So it tells us we're increasing the total amount by 50% every single day. Thus, this is going to be a result of B will equal 1 plus 0.5, which is the same as writing. And therefore, what this means is our value for I, or our model that explains this situation, is 1 multiplied by 1.5 all to the power of T. Now using this model we can perform a few analyses. So part A, determine the initial number of infections. Now the way in which we determine the initial number is we look at our graph. So our initial number of infections occurs here. Or we can have a look up here and it tells us this is our initial number of infections. Or we can do it algebraically. We can say I equals 1 multiplied by 1.5 to the power of T. Then we can say let T equal 0. Therefore we're going to get a value of 1. So 1 infection on day 1 or day 0. Part B, determine how many infections will have occurred by day 20. So with this one we could go for the algebraic method. So we can go I equals, and then I'd need my calculator for that. So I'll take it up, change this value to 20, and we'd have 3,325, 0 decimal places. Or a sensible way to do it, because the question itself does not ask or does not specify how we should solve it, we can just use our calculators. So we can say using calc, we can go into our graphing mode, then we can input our equation. So in our case it's going to be 1 multiplied by 1.5 to the power of x. Graphing this, it's going to give me some, it's not too bad today, but I'm going to fit it to this Cartesian plane here. V window 0, 6, then 0 and let's say 12. And we're looking at day 20. So we'll go back up and we'll change it to 20 seen over here. And then we'll graph it. Now we already have a little bit of foresight in that we're going to need to increase the y value because we already pre-calculated it. But if we get to this situation here where we don't see enough of the information, then we just increase the v window. So I'm going to go to say, ramp it up a fair bit, go to 4,000. Thus we can see all the way up to day 20. Solving for the value of y, we're going to go in and click ycal. It'll ask for an x value, we're going for day 20. And lo and behold, it reveals to us the information, 3,325. So this is I. So two methods we can use in this route. We can either go for the algebraic method, or if we want to go fast, we just go for the calculators. We go this method whenever we're not told to show, simply because it's quicker, less prone to error as well. Then finally C, determine on what day the virus will have infected at least 100 people. Now, looking at this, what we're doing is we're going for somewhere in here. So say in the previous question we're looking at on day, well, it doesn't really say, but what we're effectively doing is we're starting on our t-axis and we're going up. So on day 4, we're up here and then we go across. So we go day to find infection. Now we can also do this in reverse. Now for this question here, determine on what day the virus will have infected at least 100 people. We're looking for 100 on the axis here. We go across and then we go down. Now this little graph over here, it's puny, so it's not going to give us a result. So what we need to do is use our calculator. So we're going to go in, gsolve, go across. We're looking for a value of, I believe it is y. We're looking for determine on what day the virus will have infected 100 people. So we're going in, we're looking for the day. So gsolve across, we're looking for an x value. We put in 100, and lo and behold, it tells us on day 1, or when we've got 100 infected, it's on day 11.358, or let's say day 11. And we'll specify 0 decimal places. Now in summary, what we sought to do in this video was to examine or have a look at a phenomenon known as exponential growth. Now what we came to deduce was exponential growth is a situation whereby a quantity is increasing, so increasing through successive multiplication.